In an earlier lecture, we discussed how a piece of neutral matter can form an induced dipole when an external electric field is applied at the location of that neutral matter. Let's explore this further by looking at some examples involving induced dipoles. First, let's try to answer this question. A negatively charged ion is located to the left of a neutral molecule. Which diagram below correctly shows the polarization of the neutral molecule? Pause the video and take a moment to answer before you continue. To answer, it's helpful to keep in mind that the vector dipole moment P induced on the neutral molecule depends on the external electric field at the location of the molecule. Here, that external electric field comes from the ion, which we can treat as a point charge. We can sketch an arrow representing the field E ion at the molecule as shown. The field points toward the ion because the ion is negative. As we discussed earlier, the vector dipole moment P induced by this field can be described mathematically as the product alpha, the polarizability of the neutral matter, times the electric field of the ion. Now, since alpha is typically positive, then this expression tells us that the vector dipole moment P must point in the same direction as the electric field of the ion. Now, since we know that the vector P must point in the direction from the negative to the positive charge in a dipole, then we see the only diagram that represents this correctly is diagram number 4. Let's now work out a quantitative example closely related to this question. Let's assume we have a positive ion with charge Q that's located to the right of a neutral molecule, which has a polarizability alpha. The ion's electric field induces a dipole moment on the neutral molecule. Let's calculate the electric force that the induced dipole exerts on the positive ion. To start, we need to compute the dipole moment P induced on the neutral molecule, which, as we just discussed, depends on the product of the ion's electric field at the molecule times the polarizability. We'll treat the ion as a point charge with charge plus Q located a distance r from the neutral molecule. We can now use the point charge formula for an electric field to write down an expression for the vector dipole moment of the neutral molecule. Now notice the direction of the vector dipole moment points in the same direction as the electric field due to the ion, which, because the ion is a positive, treated as a positive point charge, the electric field points away from the ion, as shown. We can also directly identify the magnitude of the vector dipole moment directly from our expression for vector P. Now we're going to shift gears a bit and think about the neutral molecule as a dipole and the electric field that it exerts on its surroundings. Specifically, we're going to compute the dipole's field acting at the location of the ion. We notice that the ion lies on the axis of the induced dipole. Earlier, we discussed how to compute the electric field on the axis of a dipole. Here is the expression we found earlier for the magnitude of the dipole electric field on axis, which we're going to compute at the location of the ion. We have an expression for the magnitude of the vector dipole moment, So we'll just go ahead and substitute that in. We can simplify this a bit and end up with this result. The direction of the electric field due to the dipole at the ion will point in the same direction as the vector dipole moment P. Now we're in a position to compute the result we're looking for, the electric force of the dipole on the ion. Since we know the point charge and we know the field at the point charge, we can write this force as simply the product of Q times the dipole electric field. Since Q is positive, this means we know the direction of the force of the dipole on Q has to be in the same direction as the direction of the electric field of the dipole acting at Q. And now we can write down the magnitude of the dipole's electric force on Q as the product of the magnitude of Q times the magnitude of the dipole electric field, like this. Let's make a couple of comments. First, the force we computed here is that exerted by the induced dipole on the ion. By Newton's third law, the force of the ion on the induced dipole must have the same magnitude and must point in the opposite direction as shown. Notice that the two forces are such that the ion and the induced dipole are attracted to one another. Second, if we repeated this calculation for Q negative, that is for a negatively charged ion, we would find that the ion and the induced dipole would, once again, be attracted to one another. I recommend you make this change and go through the calculation to prove this to yourself.